Hello and welcome to today's daily Leetcode challenge. We'll be solving question 1582, special positions in a binary matrix. Binary matrix is just a matrix where the values happen to only be zeros and ones. All right, given that, let's begin the directions. So given an m by n binary matrix mat, return the number of special positions in mat. A position ij is called special if the cell of matrix ij is equal to 1 and all other elements in row I and column j are zeros. Okay, so another way to think about this is if you were to look at an intersection of a row and a column, only that position or that intersection is special only if 1 exists in that intersection only. So once again, a intersection is special if the binary value 1 only exists in the intersection itself, and everything else is zeroed out. So in the example here, we see that the special position is row 1, column 2. Column 2 does not have any more ones in it. Row 1 doesn't have any more ones in it. And so we're given the special position output of 1. In the example 2, we're given that we have 3 of these special positions, and no wonder the column and the rows are all zeroed out where the ones are blue. So we have then some constraints that m is just the number of rows, n is the number of columns, and then some constraints on the size and the values inside the matrix. All right, so how do we think about this? Well, the naive approach would be to look at all the possible ones, and you can do this by simply iterating over the whole matrix, nested for loop, 2 for loops, one of them being nested. And then upon hitting a 1, you stop iterating and you look through that whole column and through that whole row. If it is valid, then you're set. You add that, you increase the number of special positions. However, that is a complexity of, let's say, number of ones. Number of ones times n times m, which is not ideal. I wonder if there's a way to do it in simply n times m, which means that we iterate once through all of the positions and through all of the columns, and then maybe through all of the rows. That way we reduce the number of times we have to branch out and look for all the columns, through all the columns and rows. And so how would you maybe go about that? Well, if you start noticing something here, we could have some sort of structure, intermediate data structure, representing the number of, or not even the number, the valid rows and the valid columns. For example, if I was to traverse this example 1 and figure out that only one of these columns is legitimate, column index 2, I would potentially even know where or which possible rows I would have to look through, because let's say that column 0 is omitted, column 1 is omitted, column 2 isn't omitted, and on top of that, since it's a potential valid column or a potentially valid intersection, I know where my row potentially would be, because I know that rows 0 and 2 are out of the picture. They don't have any single ones in it. So in the first intersection, at the first step, I'm going to create an intermediate data structure called, let's say, valid row. What is it going to be? Valid row to column. Valid row index to column dict. This is a long name, but it's at least intuitive. I'm going to now iterate through all of my columns, right? I want to say for call index in range len mat of 0. I'm going to see if, okay, let's see, for row index, because I don't have access to the whole array right away, I actually have to go and do another loop. This is not ideal, but it'll get the job done. If, let's have a value here, mat of row index and column index, if val is equal to 1, then what do I do? So I can't just say that if val is equal to 1, then go ahead and start and include that in my valid row index column dict. I'm going to make another variable, another two variables called one's index and one's sum. If this is equal to 1, then I append 1 to this, and additionally I say that index is equal to the row index. What is this going to do for me? Well, if I traverse all of my elements in the column and find out that my one's sum is equal to, if is equal to 1, then, well, all of a sudden I know that my column is valid. So now I can append by the one's index, because that's where I kept my valid 1, is equal to the column's index. Why do I need this right here? Why do I need this map of one's index to column's index? My idea is that once I later iterate through all of my valid rows, the way that I'll know that a point is actually completely valid is if the valid row contains a 1 in the column's index place. Let me show you what I mean. I have this value right here, return 0 just for testing, and here I should get something like 1 and 2. What this 1 and 2 represents is the keys here are going to be valid rows, and only one of these rows is valid. The value is going to be like a check indicating that this row would have been valid only if the 1 exists in the column 2. Why is this important? Let's now do the same. Let's now go over these valid rows. Res equals 1. That's going to be my return value. For what am I doing? For valid row, for row index, and let's say column index. In this items, I'm now going to say that if let's get the row before row index, and now let's say if sum row is equal to 1, meaning that row is actually valid, because previously we were just looking at the rows being valid only from the point of view of a column. But now I'm actually validating that the sum of the row is equal to 1, and row index of 1 is equal to the column index, then res plus equals 1. So what this is doing is a previously considered valid row, which was just based on that a column that has only 1 in it, is now actually being considered as a valid row, thereby would have been making a valid intersection. And so I'm considering that here by checking if only one exists in that row, and the index matches up with what I previously wrote in my valid row index column dictionary. So let's check if this works, and hopefully it does. Great. Let's see how we're doing against other solutions, and we're not doing too bad. 88th percentile, almost 90th. Let's see if there's any cleaner solutions, because I do admit this is a bit messy. No. Yes. Let's see. What are they doing here? So another thing about these, this is very low code, but what is V? Okay, well, let's see what V is. If you're enumerating the matrix, then the R is just the row. If the sum of the row is 1, then the column. So this is just valid rows. What about this? Valid rows, and what are you doing here? Enumerate a zip of Does this somehow flip? Does this flip the... Interesting. I want to know this because this would be very helpful. This is a spread operator. Zip zips it with what? Hold on 1 second. By the way, this is a totally valid solution, and for those of you who don't want to keep watching, please skip this portion. But I'm interested in what this is. Zip mat return 0. I don't even know what to do. Enumerate key value and print key value. Yeah, this didn't do anything. This didn't flip. This did not flip the matrix at all. Transpose. It didn't transpose the matrix, which is, I thought, what it could have been doing. And, oops, submission. Enumerate zip mat if. How is that happening? How is he claiming that? How is he claiming that this is a So am I wrong? Did it actually flip it or transpose it? Oh, it did. It did transpose it. What? This is the column. This is the first column. 1, 1, 0 is the first column. I know what's happening. A spread operator spreads this into 3 into this, essentially. 1, 0, 0. 0, 0, 1. And 1, 0, 0. And let's see, does this give me the same result? A set of, yep, okay, perfect. Zip. This is beautiful. So I now know how to spread or transpose a array or a matrix without even needing NumPy. Cool. In that case, if you are, let's see, let's look at this solution one more time, and we might actually, I might adopt that one because it's so clean. Yes, and then for some, okay, this part I don't get. For that's a bit hard to read. For R and V, row and valid rows, for C and H, valid rows, valid columns. There could be okay, well, at least I can write it. But I don't understand why. Would there potentially be multiple? Let's rewrite this quickly. So valid rows is just equal to I for I row in mat if row if sum row is equal to 1. Let's print this valid rows. Return 0. We should just get 0, 1, and 2, and I messed something up. Oh, enumerate. Awesome, and all the valid rows are there. And actually, now that I'm thinking about it, our solution, initial one, could have actually been even faster because here you're considering all columns and rows, whereas previously we were only considering only one of the valid things. But this is very clean, and I do appreciate clean did he have this? Matt I J for I in, this is the rows for J in valid calls. Return. And I think I messed up. Oops, there we go. Yeah, this is cleaner, but it's a bit harder to understand. It's not that intuitive, and it doesn't actually work faster. So, okay, upward. Use this solution. It's cleaner, and it's not cleaner, but it does logically get the point across better. And it's probably faster, and it seems like it is. So, okay, apologies for that rabbit hole dive, but I would suggest using this. Okay, please like and subscribe. Thanks for watching. See you guys later.